Prior to ENIAC, calculations relied on manual methods or mechanical aids. The U.S. Army's need for rapid artillery trajectory calculations during World War II accelerated the search for faster computational methods. In 1943, John Mauchly and J. Presper Eckert initiated a secret project at the University of Pennsylvania. This project resulted in ENIAC, the first programmable, general-purpose electronic digital computer. ENIAC's electronic design allowed for significantly faster calculations compared to previous mechanical methods. As a general-purpose computer, ENIAC could be programmed to solve a variety of computational problems. During World War II, the computation of ballistics tables was a critical task. Human computers and mechanical analyzers struggled to meet the increasing demand for these calculations. Mauchly and Eckert envisioned an electronic machine using vacuum tubes to perform calculations thousands of times faster. Project PX was initiated in 1943 to develop this electronic computing machine. The project united technicians and engineers to address the urgent wartime need for rapid ballistics calculations. The electronic machine promised to revolutionize the speed and accuracy of ballistics calculations during the war. ENIAC occupied a large basement room and consisted of 40 metal cabinets. ENIAC contained over 17 0 vacuum tubes, 70 0 resistors, 10 0 capacitors, 6 0 switches, and 1 500 relays. The machine weighed approximately 30 tons and required hand soldering of 500,000 joints. ENIAC had no moving parts other than its vacuum tubes and required significant power and cooling. ENIAC was programmed manually by plugging wires and setting switches on panels. Each new problem required a complete rewiring of ENIAC circuits, a process that could take days. Once configured, ENIAC could perform approximately 50 additions per second. ENIAC's tasks included computing, artillery, firing tables. ENIAC was also used for Monte Carlo simulations, weather prediction, and early hydrogen bomb design. Each ENIAC cabinet measured approximately 8 feet in height. The ENIAC occupied a substantial area of 50 by 30 feet. Mapeera House, a modern building, stands at approximately 200 feet tall. ENIAC's size was dwarfed by modern structures. The ENIAC required substantial air conditioning due to its 174 kilowatt power consumption. Despite its large size for the era, ENIAC's power demands necessitated significant cooling. Operating ENIAC required a dedicated team to manage its complex functions. 6 women, formerly human computers, were ENIAC's first programmers. The women translated problems into wiring plans and switch settings for ENIAC. Programming involved manually plugging cables and setting switches on ENIAC. Troubleshooting programming errors could cause significant delays in ENIAC's operation. To maintain continuous operation, the women often worked in shifts around the clock. ENIAC's all-electronic design faced reliability challenges due to the limited lifespan of vacuum tubes. To enhance reliability, ENIAC's vacuum tubes operated at a quarter of their rated power. ENIAC consumed 174 kilowatts of electricity, generating significant heat. The substantial heat generated by ENIAC necessitated a heavy-duty air conditioning system, and operators replaced dozens of tubes daily. ENIAC was constructed using thousands of radio and telephone components. Vacuum tubes were a core component in ENIAC's design. The assembly process involved manually soldering 70 0 resistors and 10 0 capacitors. Resistors and capacitors were essential passive components in ENIAC circuits. ENIAC's panels were mounted on casters, making it a 30-ton rolling machine. ENIAC blended mechanical engineering with electronics. Completed in 1946, ENIAC's construction cost approximately $400. Nicknamed the Giant Brain, ENIAC served the U.S. Army for a decade. ENIAC produced ballistic tables and ran experiments, demonstrating its computational capabilities. ENIAC influenced the development of modern electronic computers, proving the future of computing. Vacuum tubes functioned as electronic switches in ENIAC. The glass vacuum tubes were mounted in sockets on metal frames. Resistors and capacitors were soldered around the vacuum tubes. Heavy electrical cables connected the modules, enabling electronic signal transmission. ENIAC was programmed by manually setting toggle switches and connecting cables on a plug board. Each new computational problem required a complete rewiring of the ENIAC's panels. Rewiring the ENIAC for a new problem could take several days to complete. Manual configuration was essential for directing ENIAC's computational tasks. The plug board acted as a physical interface for programming the ENIAC's logic. ENIAC's programming method contrasts sharply with modern software-based programming. ENIAC's 174 kilowatt power consumption was substantial, exceeding the needs of most buildings at the time. The high power demand resulted in significant heat generation during ENIAC's operation. A dedicated air conditioning system was necessary to maintain operational temperatures for ENIAC. Maintaining stable operational temperatures was crucial for ENIAC's reliable performance. Vacuum tube burnout was a frequent reliability issue in early computers like ENIAC. To improve reliability, vacuum tubes were operated at a reduced power level, specifically 1/4 of their rated capacity. Reducing power lowered stress on the vacuum tubes, extending their lifespan and improving overall system reliability. This strategy enabled more continuous operation of ENIAC by minimizing component failures. ENIAC achieved speeds up to 50 additions per second by utilizing all its accumulators in parallel. Parallel processing significantly enhanced ENIAC's computational efficiency. This parallel architecture made ENIAC the fastest calculator of its time. Each accumulator operates independently, allowing for simultaneous calculations. The parallel processing capability allowed ENIAC to solve complex mathematical problems much faster than previous machines. ENIAC was initially used to calculate artillery firing tables for the Army's ballistic research lab. The computer's applications expanded to include Monte Carlo simulations. ENIAC was also employed for weather prediction modeling. Early hydrogen bomb design also utilized ENIAC's computational capabilities. These diverse applications demonstrated ENIAC's versatility as a general-purpose computer. ENIAC's ability to handle varied tasks highlighted its significance as a pioneering general-purpose computer. The completion of ENIAC in 1946 represents a key milestone in computing history. ENIAC's legacy is evident in the architecture and functionality of modern electronic devices. Human ingenuity and technological advancement drove the creation of ENIAC. ENIAC played a transformative role in ushering in the information age. The impact of ENIAC continues to shape the digital landscape.